today I'd talk about this subject. Firstly, I'd like to explain why data simulation is needed. The point is that the null model is correct. The error grows exponentially due to the chaotic nature of the real world, and without data simulation, the error goes exponentially accordingly. So data simulation aims to modify the simulation state based on the observation data in order to be the simulation to follow the observation data. And in this particular example, we simulate a contaminant dispersion in city area whose simulation states are updated based on the observation data like radar for wind speed and a satellite image, for example. And the Ensemble Kalman filter or its variant is a promising approach, which approximates the Kalman filter with the ensemble simulations. In order to accelerate this type of approach, concurrency is necessary. So Ensemble Kalman filter involves computations, communications, and I/O. So senders receivers may be used for acceleration. Before moving to the senders receivers, I'd like to demonstrate the power of standard language for GPU computing, namely std_per and mdspan. In std_per, high-dimensional arrays are allocated by mdspan like this one, which is quite similar to Cocos views. And for parallel iterations, we use the std for each n, shown here. And for reduction, we use the transform reduce. And we just define the heat equation with using lambda, and with mdspans, these are quite readable and quite similar to what you may program with Fortran, for example. And actually, in addition, the performance is also good. We have measured the performance of the 3D heat equation solver on ice rate B100 and 800, and the std_per showing that is quite compatible performance with the promising approaches like Cocos, and sometimes work better. And on CPUs, there are some sort of vectorization issues, less good, but still acceptable performance. So with std_per, we can achieve performance, the portability, and readability. With senders receivers, we can even achieve the concurrency. So how to implement with senders receivers? And there are three major components in senders receivers: the scheduler, the sender, and consumer. The scheduler just defines the device, the meaning CPUs or GPUs. The senders or a sequence of senders define pipeline or lazy tasks. The meaning lazy is that the tasks is not executed instantaneously, and it is consumer that executed tasks defined by senders. So this flowchart is their 3D heat equation solver with MPI parallelization, and they're just packing and P2P and unpack, and he's sort of 3D solving heat equation. So this is achieved with senders receivers in this program. And yes, firstly, we define the sender for packing. This is achieved with the bulk sender, which is basically the same as the std for each n in the std_per. And then we will go for the then sender, which wrap the MPI communication, the P2P communications here. Correspond to this one. And after synchronization, we start the unpack sender. We start from the unpack sender, which defines the operation with bulk sender. And then go for the 3D heat equations sender and perform these operations with the synchronization. So this is quite the same as this flowchart, as you can see. Moreover, we can overlap computation and communications quite easily just by using one sender. And the packing operation is exactly the same. We then declare two senders, one for P2P and the COM sender, and another one is the inner update sender, which is the 3D heat equation sender, operating only the inner part, do not rely on the communications. And using this final sender, you are taking the COM sender and the inner update sender. This sender just perform the communication and the inner update task at the same time, as shown here, the communication and heat equation, this one. We then perform the boundary contribution by this sender, and then we got the result, exactly the same result as the previous one. So again, roughly the same as what we have in mind. So it's quite intuitive. If we then compare the performance with the other language-based model like std_per and thrust. So for the CR performance test and measured in the peak ratio, they are using the memory bandwidth achieved over the ideal bandwidth and on Ice Lake and the Harnet and MI2050X. And we got the good performance of central receivers on NVIDIA GPU, but it's less performant compared to the other frameworks on Ice Lake GPU. It's not available on AMD GPU right now. The strong scaling test, and just modifying the code from sync version to async version with minor modification, we got a 25% to 70% performance gain with overlapping in strong scaling from 16 to 64 NVIDIA 800 GPUs. It's quite a nice result. So now we are ready to move into the LETKF for 2D turbulence. So in this particular test, we are using the so-called observing system simulation experiment. In this test, we first run a raw simulation of the 2D turbulence, so-called what we call nature run, and then add Gaussian noise to nature run to create the mock observation data. The goal is just to predict the nature run simulation result with another nature run from different initial conditions using this mock observation data. This is what we call the OSSE. In this LETKF, we use the Ensemble simulation to predict the nature run from the observation data. Actually, the GPU optimization of the LETKF solver is presented in 2022 with Hasegawa-san. And in order to demonstrate the power of data simulation, we have compared the reference case without data simulation case and with LETKF. The RMSE, the error level drops quite rapidly with LETKF in time, but without data simulation, the error level is kept high. So this is the animation. And in the initial state, the error is quite high, but in instantaneously, the LETKF and reference is almost identical. While without data simulation, the error level is kept quite high. So this is the this flowchart shows the operations of the LETKF, which is extremely complicated. But basically, this consists of three parts. One is the I/O, or loading the mock observation data from file, and then communications, all-to-all communication and over Ensemble directions, and broadcast operation, because only the master rank load this file and broadcast it to all the ensembles. Other than computations, which is basically the linear algebra. Roughly speaking, and these three operations can be overlappable because in the dependency is quite these operations are independent, so we can overlap part of communications and computations and I/O. So central receivers may help. So for the first task, we have developed a performance portable version of the LETKF solver with std_per, thrust, and senders and receivers. And the left shows the LETKF solver in C++ with std_per plus mdspan. The right version is in Python. As you can see here, these are roughly identical, which means that our C++ implementation is quite readable. And the green part is written in std_per or thrust, and red part is written in the Kubras solver or Rockbras Rock solver. And the LETKF solver actually using the batched version of the gem and gemv and eigenvalue decomposition here. So this is relatively simple if you use libraries. For batched gem and gemv or matrices, or namely written in mdspans, we use the OpenMP plus eigen for CPUs. So here, just using the eigen data structure inside, using OpenMP parallelization along the batch direction. And the GPUs, and we just use the Kubras batch solver written here. For AMD GPUs, and just use the Rockbras. And And this slide shows the performance of the LETKF LBM2D solver of different problem sizes. And as you can see here in the bottom, there's the ideal performance of 2D LBM in embedded UPS, which is the theoretical performance, which can be achieved for the very simple case. But in our case, in order to get turbulence, we introduced the fourth term, which is generated by random numbers. We need to rely on Kullbass or Courant or Rockland to generate random numbers for the fourth term. So we cannot, even considering the LBM part only, we cannot reach their ideal performance in the end. So the number in the parentheses shows that in the ratio of the achieved MBUPS to the ideal performance, the 50% looks relatively low, but it's quite good. With data simulation, the performance is degraded, of course, because there's the I/O and communications. And but in the end, on the NVIDIA GPUs, the ideal performance is achieved at 8.5%, which is reasonable. And the performance drop from LBM plus data simulation is more drastic in the AMD GPUs. This is just because in the LETKF solver is more slower on the AMD GPUs due to the lower performance of batch lock solver for the agent value decomposition. And another important point is that in the I/O or some other communications or all-to-all communications or broadcast communications are quite the serious bottleneck on the NVIDIA GPUs and AMD GPUs. These figures show the breakdown on time on the ratio of each kernel inside the overall time. And as you can see, the LETKF solver is the heaviest in each case, but the ratio is quite different. And in addition, I/O are now the major bottleneck on the NVIDIA GPUs, and some communications are also quite heavy. And the AMD GPU, as I said, LETKF solver is extremely slow due to the lower performance of the eigenvalue decomposition solver. So I/O and communications are huge bottleneck on GPUs, but they are not a bottleneck on CPUs because the solver performance itself is not that high on CPUs. So introducing concurrency in LETKF solver actually helps performance quite a bit. The blue part is the asynchronous I/O task, and red part is the communications. So firstly, we got the overlapping of communications and I/O, and then we got the overlapping of I/O and the other broadcast overlapping of the broadcast operations and linear algebra showing green. So thanks to this overlapping, we got this performance gain up to 30% for most of the Ensemble sizes. Let me show you how it works. And without this optimization, the master rank start to load the data from file, which need to wait until this one. And after that, and the all-to-all communication starts, the other ranks have to wait for the master rank to join this operation. Others are secretly solved. And the asynchronous case in this program, the I/O and the all-to-all communication are executed at the same time. And also some part of LETKF solver and broadcast communications are also overlapped, which is the reason for this speed up. Let me summarize today's talk. And we have developed a performance portable version of Ensemble Kalman filter with the STD per thrust and senders and receivers. The secondly, we measured the performance. We found that in the batched version of agent solver does not perform well. And thanks to the concurrency with senders and receivers, we got roughly 30% performance gain on 100 GPUs. The future work include the pipelining task for more aggressive overlapping, and heap-based senders and receivers could be very appealing. The codes are available on GitHub. Please check out if you're interested. Thank you for listening.